Good morning, everybody, and welcome to OpenSearch Con. Awesome, great to see everybody out. Woo! As Nate mentioned, I am a Senior Principal Solutions Architect, and I work with AWS customers and have been doing this for years and years and years. Actually, been doing search also for years and years and years. And I think, I'll make the bold statement. Search is magical, right? You go to a search engine and you need something, and you go and you type a few words, and voila, like there it is. You get connected to the thing that you need. And ultimately, the search journey as a user is about getting from I need this to that's my answer. We have now a lot of stuff coming. There's the big boom in AI ML. I'm sure everybody is aware of that. You have large language models coming in that bring all of that natural language understanding or context or semantics or whatever you want to call it to help get you to the stuff you need. Chatbots, right, really caught everybody's awareness. Everybody is thinking about, wow, now I can really talk to this box sitting on my desk. Semantic capabilities are coming to the fore, and the ability to pull out that natural language stuff. So OpenSearch itself and where OpenSearch fits in the picture is OpenSearch enables you to work with the vectors that are generated from these large language models and bring them in and use them to search. These are all search capabilities. These are all related to how we do search, how you go and touch or go into the problem and pull out the solution. So, what is it really? What is search really? It's like I have this small window where I can specify what it is that I want, and I'm going to send that off to OpenSearch, and that's my means of expressing my need. OpenSearch has a pile of stuff, right? Some of that stuff is going to be the right stuff. Some of it's not going to be the right stuff. So the point is, OpenSearch should figure out which is the right stuff and send it back to me. Now, the process of figuring out what is the right stuff, that is where the relevance comes in. Relevance means that what I actually got back solves the information goal that I had. And just looking at sort of the means of doing relevance, and we're going to go through a lot of different places where relevance happens and is generated. We have standard ranking models, which is what most people think of as where do I have to go tune my relevance and tune what I retrieve. So we have text-to-text matching that's provided by Okapi BM25. We have vector similarity, we've talked about. And then we have learning to rank that provides the ability to post-filter or post-rank my results based on how people have interacted with my data in the past. So for text-to-text, we have straight-up OpenSearch. Vector, we have our KNN plugin. And user behavior, we have learning to rank. So as I said, there's the rank function itself is where you would think of as, oh, I have to go figure out how to rank my results better, right? But actually, there are many, many, many different places that lead to the end product of relevance, right? So first of all, I have my source, right? My source data itself. If it ain't in there, I'm not retrieving it, right? We have our data preparation, right? So you have some source data that's in some format, which is more or less retrievable, and you have to prepare that data and bring it in a format that it will match what your users are asking for. You have the parsing, the processing, there's enrichment, all kinds of enrichment that you're going to put and make your data better, and you're going to end up with some canonical store. In the query execution, you have not only the query coming in, but you have the ability to take that query, modify, and improve that query based on a lot of different factors. We have within OpenSearch itself, there's text, there's analysis of the query, there's matching of the particular fields and values, there is the ranking phase, and there is the re-ranking phase. And ultimately, the results go to the front end, where your front end has, again, the ability to capture how good was that result, right? So through user behavior and other signals, you should be tracking, and you should be bringing that behavior through post-processing, which is going to enable you to build better models to feed back into the query for rewriting and for improving that query. So we're going to go through a bunch of these different phases. I have here a sample of a Wikipedia dump, right? And as you can see, it is a mess. And typically, even if your data doesn't look like this, even if it comes from a database, if it's user-generated, if you crawled that data from your website, it's going to look something like that, which has all kinds of additional characters. Wikipedia has text boxes. It has section markers. So this is the raw stuff that you want to match against, right? But this is not in a format that is conducive to good matching, right? I just gave you a link there. There's all of the Wikipedia dumps are on archive.org. If you're interested, you can go pull one. You're going to pull this data either from your database, from S3, from crawling. Even if you have some canned data source or something like that, you'll bring it in that way. So we need to have JSON, right? And this is just a little code snippet. There's something Wikitext parser out there. It's an open source thing that just takes in Wikitext, chews it up, spits out text, formatted and nice with links and all of that stuff. You're going to have something like that that is going to go through and process and clean and make your data usable. It's almost always dirty. Like this is one of the things about search. There's a pre-processing phase that's always necessary. You've got bad characters in there. You've got redundant content. You've got people gaming the system by putting, keywords 800 times on the same document. And so you have to go through and clean all that stuff out. And we have this additional formatted stuff. Maybe you have a large document set that has lots of tables in it. The data in the tables is interesting. Somehow you have to parse that table or parse that data out to be able to use it for matching. So LLMs, if you're going to use an LLM for vector embeddings, they work on smaller pieces of text. This is a little code snippet that goes and looks at a Wikipedia page, and I spent some time on this, because figuring out which is the chunk that I should pick so that I would get a good vector out of it is kind of hard to automate, right? And whether you're chunking up your full document into smaller pieces so that you can do vectors on those pieces, or you're picking a representative piece, there's going to be that step to prepare for using an LLM and for generating vector embeddings. Once you have the data in some kind of format that is useful, you want to enrich it. So you want to augment with click data. That's the feedback loop. You're going to augment maybe with keywords from user interactions. If your front end is tracking, this search yielded a click for this product, if you're e-commerce, right? You want to feed that back potentially, and the keywords of the search are relevant to that document. You can put them in there, provide additional match targets. You want to augment with extracted entities, right? If this Wikipedia page is about Albert Einstein can be a keyword on that document in an entity field. You want to add embeddings, right? So you want to send it off to your LLM to generate an embedding and put it on there. We have a bunch of different ways to do this. We'll cover a little bit later. Neural plugin, there's a do-it-yourself method, and there's third-party model hosting. Now we've got our document in some kind of format, and with the right text on it, and with the right enrichment and the right embeddings, right? So let's talk about how that document is processed and how you're generating targets for matching. Because number one, if it ain't in there, you can't match it. Number two, if the text is not what the user expects, you're not going to match it either, right? So text analysis really is the process by which we take a document, which is a collection of fields, name, value, pairs, and we parse up those fields to generate matchable tokens, terms, that an end user would expect, right? So the analysis phase is totally critical to the relevance, right? You're not going to get the right results if you can't match them. And just, we're going to end up generating a field level index that leads to a posting list. Posting list is the collection of documents that have that field. Analysis is the key thing here. So if we think about query processing, we're going to go and use the same analysis, right? Why? Because we already analyzed this text. Now the thing has to match it right. We have to use the same analysis, right? So we take something like search engines, we're going to go to the posting lists, and we're going to figure out the matches, and then we're going to sort them, right? The matching here depends on the analysis and how you did that, right? So just a quick difference between keywords and text fields. Text fields are analyzed, keyword fields are normalized. Text fields are parsed into terms. Keyword fields are not parsed into terms. For text, we can apply custom analysis. For keyword, we can apply custom normalizers. And we're going to use a text type field for large blocks of text. And we're going to use keywords for smaller, mostly machine-generated text, right? So if I have my facets or whatever, those are going to be keyword fields. If I have a product description, that would likely be a text field. And looking at how we analyze text, right? The source text is on the left. So albedo of an object is extent to which it, et cetera. If we use a standard analyzer, OpenSearch comes complete with a set of different analyzers, and you can build customs. You can see that the standard analyzer is really just using white space and downcasing. The English analyzer then applies the language-aware stemming to generate some text which looks a little bit weird. And the idea here is we use English stems so that if I say something like, what's a good one? Radiation, where is it? Radiat, right? So I could say radiates, radiation, and all of them would stem to the same word. Again, the matching is the important thing there. If I'm a user and I want to find something about radiation, then I'm going to match however I spell it. All right, so jumping into text-based ranking, we have, the basic idea is if I query something like, how does albedo diffuse radiation? And I have two items in my index. One of them is albedo, the right answer, and the other is Albert Einstein. And Albert Einstein is in there because we have this diffuse and radiation, right? So we analyze the query text. That provides us with a set of target terms. We're going to match against them. We'll pull albedo, and you'll pull Albert Einstein because you matched both of them. This is where the text-based ranking comes in, because you want to prefer albedo to Albert Einstein, right? Because that more likely matches this question. Now, what makes it more likely? The insight here is, well, there's more words that match albedo than there are that match Albert Einstein, right? And so the core text ranking function for OpenSearch is called OCopy BM25, and that captures that basic idea, right? So it's probabilistic in nature. It looks at the amount of terms that match, and it looks at the value of those matches. If we look here, IDF is the inverse document frequency. What that is how many times does this thing occur across all of the corpus of documents. If I have a huge number of occurrences of this word, it's lower value, right? Just it occurs so many times, the discriminatory value of that particular term is not high. So that's why it's the inverse of the frequency. And then we have the frequency is the count in this particular document. So a very rare term that occurs a lot will generate a larger score than a very common term that occurs a lot or less, right? We have a couple of extra things in BM25 that account for, number one, the saturation. So you don't want, you don't want a single term to overwhelm the score, right? So you basically limit the impact of any particular match. And then we also have, in this document, saturation, right? So those are just limiting terms that make the match a little bit more generic and a little bit better. So when you tune for relevance and when you tune for text-based relevance, there are a couple of different times when you can intervene. At index time, you can look at the document level versus field level values of those terms. You can do boosting, you can do various things to increase that. You can use a ranking feature, bring that into your score, and increase your score based on elements of the document or elements of the overall usage of your system. So those are with the query time, function scores, and boosting. That's text-based ranking. Then we want to talk about vector ranking, right? And the basic idea is that a vector is an array of integers. That dimensionality of that vector creates a space, an n-dimensional space. Each of your documents is coded as a vector and lives as a point in that space. You take your query, you code it into that same space, and you find what's close by. A model is simply any learned model that's a function that maps a source to a destination. Large language models specifically map chunks of text into that vector space. An embedding is a vector that you add to your document that is its representation in that space. OpenSearch supports a number of different engines and algorithms, and it gets confusing, that can both store these vectors and provide similarity and matching for those vectors. And within that, we said close, right? This query vector is close to these other ones. Well, close has a lot of different definitions. We can talk Euclidean, we can talk Manhattan. There's all kinds of different distance metrics that apply within that space. When you use OpenSearch, there are a number of different ML plugins that provide the capabilities to do this kind of vector matching, right? So we have our KNN plugin, our Neural plugin, our Learning to Rank plugin, and the ML Commons plugin that all give you means of hosting machine learned models and applying them to ranking. There are a number of different ways that you get these models and build them for OpenSearch. So we have a number of different ones, LambdaMart, XGBoost, et cetera. Those will generate your models, which you can onboard either in Learning to Rank or ML Commons. So semantic search, when you want to implement semantic search in OpenSearch, there's two different ways you can do it. There's the do-it-yourself method, where you're generating the vectors yourself, and there's the Neural plugin method, where the Neural plugin takes care of a lot of this stuff. So what we have here, number one, we're going to run a batch job over our source data, and we're going to send that data to an LLM. The LLM could be in SageMaker, could be third-party. This is all in your own code base. You're building these vectors. And then we're going to store that vector into OpenSearch along with the document having enabled the KNN plugin. Your client submits a search request. Again, you're going to call to that model to generate the vector for that request. You're going to send that request to OpenSearch, which will take that vector and with KNN, or with KNN in this case, compute the distance for that vector, give you a set of results that's scored based on how close they are. With Neural Search, it's more simplified. The Neural Search plugin automates the process of sending data to that model, whether it's hosted locally or hosted in a third party, and it automates the process of sending the queries. So you just send your queries to OpenSearch, you just send your documents to OpenSearch, Neural Search takes care of doing the work of the embeddings. So with the Neural plugin, you're going to load your model, and then, so you have to load the model into OpenSearch. Then in your mapping, you'll define a field, which is a vector field. A lot of different parameters on that field itself. Most important, you have to set the dimensionality. The dimensions have to match the dimensions that the model's producing. You've got your mapping. You add an ingest pipeline that engages with the neural processor that's going to tell neural search which field do I map on, which source field of text do I send for embedding, and then which field should I put that in on the search document. So it's just a regular ingest pipeline and engages with the neural plugin. And then at query time, you use a neural query. You specify, in this case, the plot embedding field. Your query is going to be query text here. And neural search plugin sends that off, does the embedding, retrieves you the ranked results that are distance-based. I will do a little commercial. Friday morning, we have a workshop, which is hands-on, where you can try all of this out. You'll build a little sample app that's called Movie Geek that enables you to search movies. That's the registration link. So anybody who's interested, we welcome you to come and participate. Once you have the search results in front of your end user, you want to capture what that user does with those results, because you're going to feed that back and augment your documents, augment your queries, make your whole relevance experience better. So on the query side, you have searchandizing, so finding landing page for brands and categories and seeing that people interact with them. You always want to examine your search logs. You want to look at the head queries. These are the top 100 queries. And you always want to look at the long tail. You want to do sampling and find out what are people searching for that's kind of unique, and evaluate whether your results actually solve those problems. Because here's the thing, relevance is a person-specific or a person-relative measure. So there are automatic measures, there are things you can measure, but ultimately it's a person who decides whether something is relevant. So you can look at those queries and say, hey, somebody searched for, I don't know, how does diffuse radiation affect the temperature of the planet, something like that. Really long query, probably not many of those. And you can look at your result and say, yeah, where do I need to adjust here? How do I make my results better? And query rewrite is part of that. And again, in the click stream, you want to enrich the documents with clicks and purchases, any other signals that are user interaction that say this query and this set of results, the users preferred this one. And whatever the signal is, they clicked on it, they bought it, et cetera, right? You always want to look at your zero result queries. A zero result query means you didn't have the thing that they were searching for, or the way that they searched for it was not something that you supported. Examine those, figure out what's going on, correct broken links. Did somebody click on a result that went nowhere? We have to go fix that, right? And it's possible to do this as single session, but it's better if you can do multi-session. You can pull out information that looks like a trail of searches. Like I searched for this, that wasn't quite right. I changed my query to this, that was better. I changed my query to this, and eventually I clicked on something. So you can pull information out of that chain of searches that tells you what was the original query and how do I link it better to the search result that they eventually clicked. Right? You also want to track particular users, right? So if this user always clicks on Nike, then that user should get a boost for their queries for Nike, right? You want to look at the query to clicks and capture for this user and enrich the document so that for that user you can boost and you can do for all users as well. And then dwell time is one that it's a tricky metric, but it's interesting, especially if you have an information kind of system. Like, did somebody actually go and read an article that you recommended and stay on that page for 15 minutes, right? That's kind of another signal that that was the right search result for that query. And of course, you want to feed all of this back into learning to rank. With learning to rank, you make judgments about particular queries and particular documents. And you build a golden set of these documents are good results for this query. You add additional features. This is like Wild Wild West here. You can add most anything as additional features to this process. And then you want to send it through an ML model that's going to build something that you can load into OpenSearch. Again, XGBoost, LambdaMart, RankLib. And then you perform your search with LTR, learning to rank. Learning to rank is a post ranker, takes the output of the initial ranking phase, applies this modeling, and then re-ranks the results to better match the user behavior. So this is a simple way to get started. So if we look at how search is evolving, 10 years ago, the typical search was 2.3 terms, right? People were using search engines and they were really conscious of, I need to match these two words, or I need to type these two words to get a good match. Along the way, we added faceting. Faceting, if you don't know, is the set of attributes and values that you see in the left rail that enable you to click on brands or colors or sizes or what have you, so that not only is the 2.3 words, it's like I click in and I say I want Nike, right? And funny enough, facets are what grew into all of the analytics capabilities of OpenSearch. But then, 5 years ago, people were more asking questions. You saw queries that looked more like, how do I do this? Or what do I need for that? And now, with the advent of chatbots and large language models, we're seeing things that are more conversational. And I think in 5 years, the search result that looks like 10 items with a clickable blue link is a thing of the past. I think we're going to a world where your interaction with a search engine is going to be conversational. You're going to talk to it through a chatbot. And it comes back to the original point of the magic is finding the thing I need. And if I have a tiny text box to type a few words, that's hard. If I have a conversation, I'm more likely to get to the right thing. So I think that that's where we're headed. And I think also we're looking at right now an OpenSearch, which is a monolith that encapsulates a lot of these phases that we talked about, the analysis, the ranking, the re-ranking. And I think we're headed to a world where you're going to have multiple systems that interact with the query, because we talked about a lot of the different information that comes into how to process that query, how to improve that query, how to make that query more true to the intent of the user and what we have in the stuff, right? So we're going to have multiple query systems that are going to engage and work on that query. We're going to always have a need for some kind of matching, right? So you're going to have OpenSearch. OpenSearch is going to do your matching at least, right? Post-matching, you're going to have multiple systems, again, that take the user behavior, that take other signals and can re-rank based on working with those signals, right? So I think the monolith, we're headed towards a world which is not a monolith. And I think this is true for many, many large-scale systems, search systems, that they exist in this ecosystem, right? And ultimately, we'll have generation and summarization and something that, again, reduces that 10 items down to 1 item with or without a clickable link. Wanted to give you a couple of links. And thank you.